Alright, today's lesson is about algebraic and geometric proofs. You're going to need your workbook and open it to page 35, and we're going to begin taking notes there. So go ahead and get your notebook, your workbook and something to write with. Alright, so the first things first is what kind of justifications can you use in writing algebraic and geometric proofs? We're going to talk about different properties of equality. You can see that on your page as well. But before we do that, let's talk about the definition of a proof. Okay, a proof is a logical argument. So this is the reason why we've been discussing logic, deductive, and inductive reasoning. We're going to be using all of those techniques in our proofs. So basically, we're proving something, we're making an argument and stating a sequence of statements to prove it. So do you remember in inductive reasoning I told you that if you had a conjecture, you either needed to prove it true or you needed to find it false by counterexample. It's much easier to find something false by a counterexample than to prove it. But we are going to learn how to prove it. Now, once we have a conjecture and we prove that it is true, we call this a theorem. Okay? Remember that theorems are different from postulates, and we'll talk about that in just a minute. Alright, so here are the properties of equality that I was talking about. Okay, you've got the addition property, which means that if A equals B, then A plus C equals B plus C. Okay, so that's like saying if I have X equals 4, then I can say X plus 2 equals 4 plus 2. You can add something to both sides of the equation. A lot of times we use this when we're solving for X. If we have X minus 2, let's put an example, X minus 2 equals 6, we would add 2 to both sides. That's what we call the addition property of equality and get X equals 8. Alright, the subtraction property of equality is basically the same thing except for instead of adding C, we are now subtracting C. Multiplication, instead of adding or subtracting, this time we multiply by C. And divide by C, that would be the division property. Now the reflexive property sounds very silly, but this is actually something that we're going to use a lot when we talk about triangles, okay? A equals A. So if I have two triangles that share a side, okay, so let's call this triangle A, B, C, okay? ABD and CBD share the side BD by what we call the reflexive property, okay? So that sounds silly right now, but we will be using it a lot in the future, okay? Now the symmetric property says if A equals B, then B equals A. We can just switch them. It's basically a mirror image. It's symmetrical. Alright, now the transitive property is very similar to when we talked about the law of syllogism. When we said that P implies Q and Q implies R, we can say that P implies R. This is saying if A equals B and B equals C, then A has to be equal to C. Okay? And the substitution property of equality, it says if A equals B, then I can substitute B in for any A. Okay? And we did a little bit of that previously. But we will use this, we will refer to this chart frequently, so make sure you have it handy. Alright, it says given the equation 3 equals x minus 2, you quickly write the solution as x equals 5. What property or properties did you use for this? Well, first off, you would need to add 2 to both sides, so that is the addition property. And notice that it says x equals 5, not 5 equals x, so we actually are using what we call the symmetric property. Alright, so give an equation of an example of an equation that you can use to solve by using the division property of equality and explain how you would do it. So here's my example, 2y equals 6. I would need to divide by 2 in order to solve and get y equals 3. Okay, so that is the division property in an example. You can pick your own example, but there's mine. Alright, so the proof Alright, here we have the proof process. Okay, step 1 says to write the conjecture that needs to be proven. I will say, given this, prove this. So you need to write what you are trying to prove at the top. This is your goal in mind. Number 2, draw a diagram to represent the hypothesis of the conjecture. Occasionally it'll be representing triangles or angles. Drawing a picture is going to be your biggest help. Now in the given, you're going to be given some information. Go ahead and state that information in your proof and mark it on the diagram. Then you are going to state the conclusion of the conjecture in terms of the diagram. Plan your argument out very thoughtfully and then prove it. So, another word that we need to know is the postulate. Remember, a postulate is something that we accept to be true. We've already talked about the angle addition postulate and the segment addition postulate. I'm not going to ask you to prove these things. These things are considered true without proofs. Just like we know that 1 plus 1 is 2, I'm not expecting you to prove that. Okay? So that's the difference between a theorem that needs to be proven and a postulate that is true without a proof. Now you'll see that I've highlighted here the 2-column format. Okay, 2-column proofs are one of the most common types of proofs, so we will begin with this. Alright, so this proof says if A, B, and C are collinear, meaning collinears on the same line, with AC equal to BD and AB equal to CD, complete the proof by the missing statements and or reasons. Alright, so we are given that AC equals BD. So A to C is equal to BD. These two are equal. Put the little tick marks. And then we need to prove AB is equal to CD. So we need to prove that this piece is equal to this piece. Alright, so the first thing we need to do is state what we are given. So AC equals BD. That's given. Now take a look at this. It says AC is equal to AB plus BC. AC is equal to AB plus BC. Well, that looks like my segment addition postulate. And it is. Alright, and the same thing. BD is equal to BC plus CD. Now, we said that AC equals BD. There is some substitution that can happen here. So we're going to write that AB plus BC actually equals BC plus CD. Because AC and BD are the same, I can set these equal to each other. Alright, now you subtract BC from both sides and you're left with AB equals CD. So this is the subtraction property. And that's the end of the proof. So for example number 2, it says in the figure X is the midpoint of WY. So WY, there we go. And Y is the midpoint of XZ. So this and this. Notice that XY is the same length as WX and XY is also the same length as YZ. What that means is that all three pieces are the same length. So we would prove it by the definition of a midpoint, and we would say that WX equals XY by the definition of a midpoint, and XY equals YZ by the definition of a midpoint. Therefore, we can say WX equals YZ. So by the transitive property, we can say that WX is equal to YZ. Alright, so I have a fun little tidbit that I'm throwing in today's video. I know that I have mentioned briefly about my trip to Japan. I was there for 3 weeks as part of a study abroad class in college. So take a minute, pause if you want to, look over some wonderful, great pictures. You'll see a few of them include me when I was in college, so I know I look a lot different than I do now. Alright, so you should be on page 39 now of your book. Okay? And we're going to begin talking about geometric proofs. First things first, we need to talk about some words here. Opposite rays are two rays that have a common endpoint that make a straight line. So if this is a point, here we have a ray here, and this ray here. These two rays put together make a straight line. So I would call those opposite rays. Now a linear pair is a pair of angles that are adjacent. So for example, in this picture, a linear pair of angles would be KJM and LJM. Notice they're not congruent, however, by the angle addition postulate we can say that they add to 180 degrees. Okay, that's what's special about a linear pair. Remember, complementary means adds to 90, supplementary means adds to 180. Alright, just reiterating that. Complementary adds to 90, supplementary adds to 180. Alright, so here we have a linear pair theorem. We need to prove that these two angles will add to 180 degrees, because that is the definition of supplementary. So instead of actually doing the full proof, we are just going to develop a plan, and then in part B we will do the proof. So since it is, we are given that MJK and MJL are a linear pair of angles. We know that JL and JK are opposite rays, and that opposite rays form a straight angle. The straight angle must be 180 degrees. Therefore, by the angle addition postulate, MJK and MJL must add to 180 degrees. So what we have here is we need to fill in the reasons. First and foremost, we are given that the two angles are a linear pair. Okay, the definition of opposite rays is that they form a straight line. So that's your reason for step 3. We know that LJK is 180 because that is the definition of a straight line. And that when we add them, they equal the big angle LJK. That's your angle addition postulate. And then last but not least, by substitution, whoops, if I could spell it, substitution property, we see that they add to 180 degrees. And the definition of supplementary angles is that they add to 180 degrees. So I'm cross out all of them, we use them. So basically you got some training wheels here. You are putting in the blanks for the reasons and following along with the proofs. Okay, by the end of us learning proofs, you will be able to do proofs by yourself without training wheels and starting from scratch. Alright, so we have some reflection questions here. Is it possible to prove the theorem by measuring MJK and MJL in the figure and then showing that the sum of the angles is 180? Well, they're saying use your protractor, measure it, and it adds to 180. Well, here's a problem. You've proved it for that specific set of angles. You did not prove it for all angles. So the answer is no. Alright? So fill in 1A. 1B says the proof shows that if two angles form a linear pair, then they are supplementary. Is this statement true in the opposite direction? So what we're saying here is we want to know the converse. If two angles are supplementary, are they a linear pair? Do you see how we're using logic here? We're wondering, is the converse true? Okay? So you'll see that I've drawn two angles here. These two angles are supplementary. However, do they form a linear pair? The answer to that is no. So the converse is not true. So you need to say that the angles below are given an example. Remember, to prove things false, you only need one counterexample. It's much easier to prove things false than it is to prove things true. Alright, here's a you try question. I'd like you to pause the video and then try it and then check back with your answer. Alright, so here is the completed proof. Now this is very important. We will be using vertical angles over and over and over again. Vertical angles are these angles right here or this pair of angles right here. Notice that they are directly opposite of each other. They are made by two lines. Okay? Vertical angles is very important. Now that we have proved these true, we can use this in the future. Alright, well that's all we have for today. I will see you later.